You are sitting in a quaint room. The walls, the furniture, the air around you all appear stable, fixed, and continuous. You can reach out and touch a book, see the light shift across your desk, feel the flow of seconds as you breathe. The sky outside seems vast, but measurable. You assume that what you see, the galaxies, the stars, the cosmic background of faint radiation, is almost everything there is. It is what science has allowed you to map, to catalog, to measure. Yet, the universe you inhabit is profoundly more empty and simultaneously more full than these observations suggest. From the faintest flicker of light to the gravitational tug of invisible structures, the majority of what exists is beyond the reach of your senses and even your instruments. You can measure it only indirectly, through its absence, or through effects that contradict every intuitive assumption about space, matter, and causality. The question that emerges is precise, unavoidable, and deeply unsettling. Why can you see so little of the universe, when the universe itself is so vast, so full, and yet so silent in its presence? The observable horizon. Everything you can see in the universe is limited. Even with the most powerful telescopes, there is a boundary, a horizon beyond which light has not yet reached you. This boundary is not a wall, but a consequence of time, distance, and the finite speed of light. Beyond it, there may be infinitely more, entirely invisible to every method you possess. The universe appears complete, but it is only partially illuminated. You naturally assume that what lies beyond your observational reach is a distant repetition of what you can see. Galaxies, clusters, and cosmic filaments might continue indefinitely, forming patterns similar to those already mapped. But the horizon imposes a strict limit. You cannot confirm or deny what exists beyond it. No matter how sensitive your instruments become, no signal can travel faster than light, and the universe has existed for only so long. That means there are regions of space whose light has not yet had time to reach you, regions whose existence you infer mathematically, but cannot observe directly. The observable horizon is defined by this limit. Astronomers often refer to it as the cosmic light horizon. It is not a physical barrier, not a sudden edge to the universe, but a boundary of perception. The further you look, the closer you approach the universe's past, because light takes time to travel. A galaxy 1 billion light years away appears to you not as it is today, but as it was 1 billion years ago. Every observation is a glimpse into the history of the cosmos, and the horizon marks the oldest history you can access. Beyond it lies a reality forever obscured, whose properties might be radically different from the regions you observe. the implications are profound. You tend to think of the universe as continuous and complete, but your observations are inherently partial. The light you detect originates only from regions whose age and distance satisfy a simple rule. They are close enough for their light to have arrived. All other regions are, for now, invisible. There may be structures larger than anything in your observable universe, vast arrangements of matter and energy whose effects do not yet reach your instruments. The known universe, the one you map with surveys and telescopes, is merely a bubble within a much larger, potentially infinite expanse. This limit also affects the interpretation of uniformity. The cosmic microwave background, the afterglow of the Big Bang, appears nearly identical in every direction. This uniformity suggests a level of homogeneity across the observable universe, but it does not guarantee that the unobservable regions share the same properties. Beyond the horizon, the laws of physics may operate differently, or conditions may have evolved along a path entirely distinct from the one you can measure. The observable universe gives the impression of completeness, yet it is only a fraction of the total reality. The observable horizon also defines your ability to measure cosmic evolution. As galaxies recede due to expansion, more of them will eventually cross beyond the horizon. Light emitted today from these distant regions will never reach you. You are watching a universe in which visibility is gradually disappearing. What you perceive as vast and rich will slowly become less accessible. The horizon is both a window and a cage. It allows observation, but also imposes a strict limit on certainty. Even theoretical models cannot fully circumvent this boundary. You can extrapolate beyond the observable universe, but such extrapolations are constrained by the assumption that conditions continue as observed. Every equation, every simulation is tethered to data you can measure. Beyond the horizon, the universe may contain surprises, contradictions, or phenomena entirely unanticipated. You are limited not by imagination, but by physics. The observable horizon is the final arbiter of knowledge, a natural barrier built into the fabric of reality itself. In the end, the observable horizon is a subtle but profound reminder. Most of the universe lies permanently beyond perception. The cosmos is far larger, far stranger, and far more unknowable than the patch of light you can see. What you perceive as the universe is a fraction of the whole, a fragment illuminated, while the vast majority remains cloaked in darkness, forever beyond your reach. The certainty you feel from observation is constrained, provisional, and quietly incomplete. The missing mass problem. Galaxies, rotate with speeds that cannot be explained by the stars and gas you can measure. The stars move faster than visible mass allows. The missing mass is inferred through gravitational effects, not by direct observation. You are compelled to accept the presence of something you cannot see, something that dominates the dynamics of the universe, but remains undetectable in any conventional sense. When you observe a spiral galaxy, you expect its stars to orbit according to a simple principle. The closer the star to the center, the faster it moves. The further away, the slower. This principle, derived from Newtonian mechanics, accurately describes the solar system, where planets follow predictable paths around the sun. But in galaxies, this law fails in the outer regions. Stars at the edges orbit far faster than the visible mass of the galaxy should allow. The acceleration of these stars implies far more mass than you can account for. And yet, no light, no radiation, and no detectable matter corresponds to this mass. This discrepancy forces a difficult conclusion. The universe is not composed solely of the objects you can detect. Most of the mass influencing motion is invisible. You do not see it directly. You do not measure it through emitted light, yet its gravitational pull is undeniable. Every measurement, from the rotation curves of individual galaxies to the dynamics of galaxy clusters, consistently points toward the same result. Most of the matter in the universe is hidden. You are confronted with a reality in which the majority of mass is entirely beyond perception. Clusters of galaxies reinforce the problem. Individual galaxies are bound together not just by their visible stars, but by an additional gravitational glue. When you measure the velocities of galaxies within a cluster, they move too fast to be held together by observable matter alone. Similarly, hot gas between galaxies emits X-rays that indicate a certain mass is present. Yet the total mass needed to bind the cluster exceeds the sum of stars and gas. Once again, you confront something unseeable, inferred entirely from the motion of objects that you can observe. Gravitational lensing adds further confirmation. When light from a distant object passes near a massive galaxy or cluster, it bends in a way predicted by Einstein's theory of general relativity. The amount of bending is directly related to the total mass present, regardless of whether it emits light. Observations consistently show that the visible matter accounts for only a fraction of the lensing effect. The rest is invisible, pervasive, and unavoidable. You can calculate its distribution, map its influence, but you cannot directly detect it. The universe is structured around something that does not interact with light in any ordinary way. The nature of this missing mass, what you call dark matter, is a question without a conventional answer. It does not absorb, emit, or reflect electromagnetic radiation. It does not interact strongly with known particles. Its existence is derived entirely from its gravitational influence, and yet it dominates the mass budget of galaxies, clusters, and the large-scale structure of the universe. You are forced to acknowledge a fundamental gap between what exists and what you can see. Reality includes entities that are real, influential, and omnipresent, yet entirely invisible. This realization reshapes your assumptions about matter and presence. Most of the universe is not only unseen, but fundamentally undetectable in the way you normally experience physical objects. The stars, the nebulae, the familiar luminous structures are minor components within a far larger, darker framework. Your perception of the cosmos, based on light and ordinary matter, is misleading. The true gravitational skeleton of the universe is invisible. It forms filaments, halos, and clusters that dictate motion and evolution, yet it remains imperceptible except through indirect effects. The missing mass problem is not an anomaly or an error in measurement. It is a precise, repeatable observation confirmed across independent methods and scales. Every galaxy, every cluster, every large-scale survey reinforces the same conclusion. You live in a universe where the majority of mass is hidden, a reality dominated by something beyond conventional detection. Your knowledge is constrained not by ignorance, but by the limits of physical interaction. Most of what shapes the cosmos is fundamentally unseeable, and the universe as you know it is only a small fraction of what actually exists. Dark matter as a shadow. Dark matter is not material in the sense you experience. It interacts weakly, almost silently, with the universe you can observe. You detect it through distortions in light or deviations in orbital motion. Its presence is certain, yet it remains fundamentally unobservable. Most of the universe exists as shadow, affecting reality without ever manifesting as something tangible. When you observe a galaxy, you see luminous matter, stars, bandas, dust. But the visible mass accounts for only a fraction of the gravitational effects required to hold the system together. Galaxies spin too fast. Clusters of galaxies resist dispersion, and light bends around regions far more than the observable matter can explain. This invisible influence is not conjecture. It is a measurable effect, repeatedly confirmed. Yet it comes from nothing you can directly detect. Dark matter acts like a scaffold, a hidden frame on which the visible universe is built. You might imagine matter as something solid, something with which you can interact directly. Dark matter defies that intuition. It passes through ordinary matter without collision, does not scatter light, and cannot be captured in a container or visualized with conventional instruments. Its presence is inferred entirely from its gravitational imprint. The universe you see, the galaxies, the clusters, the cosmic web, is only a small, luminous fraction of what actually exists. Most of reality is a silent, pervasive structure, influencing motion, shaping formation, but never revealing itself to your senses. Gravitational lensing makes this shadow tangible in an indirect way. When a distant galaxy aligns with a massive foreground object, light bends around the mass. The amount of bending depends on total mass, visible and invisible. Observations consistently show distortions far stronger than the luminous matter can produce. You see the effect of something massive, yet invisible. You measure its contours, trace its presence, and map its distribution, all without ever detecting it directly. The shadow is real, and it defines the universe's architecture. Dark matter is not uniform. It clumps into halos surrounding galaxies, fills filaments of the cosmic web, and influences the evolution of structure over billions of years. These invisible components dictate the formation of stars and galaxies, control the motion of clusters, and maintain the integrity of the universe on the largest scales. Your instruments reveal its presence only because ordinary matter responds to its gravity. But the matter you perceive is subordinate to the invisible majority. The luminous universe is a trace, a faint signal embedded within a deeper, unseen framework. The implications extend beyond galaxies. On cosmic scales, dark matter shapes the large-scale distribution of matter. Voids, filaments, and walls form along its contours. Every structure, from the smallest dwarf galaxy to superclusters spanning hundreds of millions of light years, is molded by a force you cannot directly perceive. The universe is dominated not by light or ordinary matter, but by a form of reality that exists in absence, a shadow that gives shape, mass, and direction, but never reveals itself fully. Even the search for its composition underscores the paradox. Dark matter cannot be accounted for by any known particle in the standard model of physics. It is elusive, not because it is rare, but because it interacts so weakly that conventional detection is almost impossible. Every experiment designed to observe it in a laboratory has failed, yet its gravitational fingerprints are undeniable. You live in a universe where the majority of mass is unseeable, untouchable, and fundamentally alien to ordinary perception. Ultimately, dark matter reframes what you consider real. The luminous universe is the visible tip of a vast, silent iceberg. Most of existence is shadow, shaping reality without ever manifesting tangibly. Gravity exposes the presence of what you cannot see, forcing you to recognize that the universe is not composed primarily of what you can detect, but of a hidden majority that is as real in its effects as it is invisible in substance. You inhabit a cosmos in which the ordinary and observable are subordinate to the unseen, a shadow universe on which all visible structures depend. Dark energy and the accelerating expansion. The universe is not just expanding. Its expansion is accelerating. You might assume this is a minor effect, but the measurements are precise. The force driving this acceleration is dark energy, an invisible, pervasive influence that comprises roughly 70% of the total energy in the universe. You cannot see it, cannot touch it, cannot measure it directly. Yet it dictates the ultimate fate of everything around you. The discovery of this acceleration came from observations of distant supernovae, exploding stars whose brightness provides a standard measure of distance. These measurements revealed that galaxies are not merely receding from each other, as Edwin Hubble first noted. They are receding faster over time. The rate of expansion is increasing. The data is robust, repeated across independent observations, leaving no room for ambiguity. The universe's large-scale dynamics are dominated by a force entirely invisible and undetectable except through its gravitational consequences. Dark energy is uniform. Unlike matter, which clumps into galaxies, clusters, and filaments, dark energy pervades space evenly. Its density remains approximately constant even as the universe expands, a property that differentiates it from all known forms of energy and matter. It exerts a repulsive effect, counteracting gravity on cosmic scales. Every galaxy, cluster, and filament feels this force, pulling the universe apart, stretching the fabric of space faster and faster. Yet this force is entirely hidden from direct perception. You cannot see it in the glow of a star, feel it in motion, or detect it in the laboratory. Its presence is inferred solely through its effect on cosmic expansion. The implications of this acceleration are staggering. As the universe expands, more regions move beyond your observable horizon. Galaxies that are currently visible will eventually recede faster than light can traverse the intervening distance. Their light will never reach you. Over immense timescales, the observable universe will shrink, leaving only local structures gravitationally bound, surrounded by a dark, empty expanse. The majority of galaxies, clusters, and cosmic filaments will disappear from perception, hidden forever by expansion. Dark energy ensures that the universe you can observe is only temporary, a fleeting window into a much larger reality. Dark energy also challenges assumptions about causality and balance. Its uniform influence suggests that most of the cosmos is dominated not by the mass you can detect, but by an invisible, repulsive energy. The luminous universe, the structures you can see and measure, is subordinate to this hidden force. Ordinary matter, including stars, gas, and planets, constitutes a minority in the energy budget of the cosmos. You exist in a universe where the visible is a trace component of reality, structured and eventually overwhelmed by the invisible. Attempts to explain dark energy are incomplete. The cosmological constant, a term in Einstein's equations, provides a mathematical representation, but does not explain its origin. Alternative theories suggest dynamic fields or modifications of gravity, but none resolve the fundamental paradox. Most of the universe's energy is unobservable, and yet it controls cosmic destiny. Every calculation of future evolution, from the dispersal of galaxies to the fading of starlight, depends on a component you cannot measure directly. Your understanding of reality is constrained not by ignorance, but by the universe's structure itself. Dark energy also links to the nature of space and time. It is a property of the vacuum, a subtle tension in the fabric of space-time. Space itself carries energy, and this energy influences motion and structure. You live in a universe where even nothing is something, where empty regions exert measurable influence, shaping the expansion of all that exists. The cosmos is not an inert stage, but an active participant in its own evolution, dominated by invisible forces beyond ordinary perception. Ultimately, dark energy reinforces a profound truth. Most of the universe is inaccessible, intangible, and alien to direct observation. What you see, the galaxies, clusters, stars, and nebula, is only a fraction of the total reality. The majority is hidden, pervasive, and controlling, expanding space itself, pushing everything outward, and silently dictating the universe's fate. The cosmos you inhabit is temporary, partial, and subordinate to forces that cannot be sensed, measured, or seen, revealing that most of reality exists beyond the reach of human perception. The cosmic microwave background. A faint, uniform glow suffuses all of space. This relic radiation comes from a time when the universe was dense and opaque. It is the oldest light you can detect, but even it carries the imprint of regions now forever unreachable. The light is a ghost of an early universe, mapping structures you cannot access and revealing a cosmos far more extensive than your observational reach. When you measure this radiation, you are observing the universe as it existed roughly 380,000 years after the Big Bang. At that time, matter and radiation were tightly coupled in a dense plasma. Photons could not travel freely, constantly scattering off charged particles. As the universe expanded and cooled, protons and electrons combined into neutral atoms, and photons decoupled, streaming freely through space. The light you detect today is this decoupled radiation, stretched by cosmic expansion into microwave wavelengths. It is not just light. It is a direct message from an epoch before stars, galaxies, or planets existed. The cosmic microwave background, CMB, appears remarkably uniform, varying by only 1 part in 100,000 across the sky. This uniformity is striking because regions separated by vast distances could never have exchanged information or energy in the early universe. The horizon at that time was small, meaning distant patches were causally disconnected. Yet the temperature of the radiation is almost identical everywhere. You observe similarity where no interaction should have been possible, a subtle contradiction embedded in the fabric of space-time. The CMB also carries fluctuations, tiny variations in temperature that correspond to regions of slightly different density in the early universe. These fluctuations are critical because they seeded the formation of galaxies and clusters. By mapping them, you infer the large-scale structure of the cosmos, even in regions you cannot directly see. The radiation encodes information about gravitational wells, voids, and the distribution of both ordinary and dark matter. It is a cosmic imprint, a pattern left by structures beyond your observational reach. These patterns also reveal more profound truths. The light comes from a spherical shell centered on you, the limit of your observable universe. Every direction you look is constrained by the distance photons have traveled since decoupling. The radiation is a snapshot of a universe that is simultaneously old and expansive, showing structures that no telescope can resolve today. What you see is a fraction of reality, a thin slice illuminated by photons that have survived billions of years, while the rest remains hidden, forever beyond the horizon of direct observation. The uniform glow and the subtle anisotropies of the CMB force you to confront the scale of the unobservable. Beyond the reach of this relic light, entire regions of space may exist with different initial conditions, different histories, or different emergent structures. You are limited not by technology, but by the fundamental nature of causality and light travel. Every measurement you make is constrained by the fact that the universe has a finite age and that photons move at a finite speed. The observable universe is only a bubble within a much larger, potentially infinite cosmos. Even the precision of modern measurements by Kobe, WMAP, and Planck cannot bridge this gap. You can map fluctuations down to micro-Kelvin differences, trace the fingerprints of dark matter and dark energy, and infer the density and composition of the cosmos. Yet all of this is a reconstruction based on photons that have traveled from the edge of the observable universe. What lies beyond is inferred, not seen. The CMB confirms that most of the universe is inaccessible, a vast realm whose structures and conditions remain permanently hidden. Ultimately, the cosmic microwave background is both illuminating and haunting. It provides a window into the universe's infancy. Yet every observation is constrained by distance, time, and causality. The light you measure is a ghost, carrying messages from regions that are now forever unreachable. It is a reminder that the universe you can observe is only a fraction of what exists, and that most of reality, the majority of space, matter, and history, lies silent, unobservable, and beyond your reach. Large-scale structures. Galaxies are not scattered randomly. They form filaments, walls, and voids on scales that dwarf your local neighborhood. The most massive structures observed stretch across hundreds of millions of light years. Yet even these titanic formations are islands within a void that may extend indefinitely. You measure order, but the universe remains overwhelmingly empty and largely invisible. When you map the positions of galaxies across the sky, patterns emerge. Clusters of galaxies are linked by long, thin filaments of dark matter and gas, forming an intricate cosmic web. Between these filaments lie immense voids, regions with very few galaxies, spanning tens to hundreds of millions of light years. The web is the skeleton of the universe, a structure dictated not by stars and visible matter, but by the invisible scaffolding of dark matter. What you see, the galaxies, clusters, and glowing gas, is a trace embedded within a far larger, unseen framework. The largest known structures, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall, challenge expectations of scale. These formations stretch across distances so vast that light from one end has taken billions of years to reach the other. Yet even these structures are isolated within regions of space that may continue indefinitely, largely empty and beyond the reach of observation. The universe, on its largest scales, is not a uniform field of stars, but a complex arrangement of matter and emptiness, dominated by invisible mass that defines motion and shape. This distribution is not arbitrary. Gravity guides the evolution of the cosmic web. Tiny density fluctuations in the early universe, imprinted in the cosmic microwave background, grew over billions of years into filaments, walls, and voids. You observe these structures today, but what you see is only the fraction illuminated by stars and glowing gas. Dark matter constitutes the majority of the mass in these formations, yet it is entirely unobservable except through its gravitational influence. The universe's largest patterns are shaped by something that never emits light, never interacts electromagnetically, and yet controls the formation of everything visible. Voids, which dominate volume, are particularly striking. You might assume that emptiness is trivial, but these regions dictate the dynamics of surrounding matter. Galaxies at the edges of voids accelerate outward, drawn along filaments or away from the sparse interior. The voids themselves are largely undetectable in isolation. Their presence is inferred by the absence of light and matter. Most of the universe exists in these voids, silent, empty, and unobservable, except for their gravitational effects on luminous structures. Large-scale structure also reveals the limits of perception. Even with extensive surveys, such as the Sloan Digital Sky Survey, you cannot map the entire cosmos. Observational horizons prevent you from seeing structures beyond a certain distance. Simulations suggest that the cosmic web continues indefinitely, forming a vast, complex network of filaments, clusters, and voids stretching beyond the edge of the observable universe. What you can detect is only a small fraction of the total arrangement, a luminous tip embedded within a much larger, invisible framework. These observations redefine your understanding of scale. The structures you can see are enormous, yet they are minor components within a universe that is mostly empty space, shaped by invisible mass and extending beyond perception. The apparent order masks an underlying vastness that is largely unobservable. The cosmos is structured, but overwhelmingly inaccessible. The majority of space contains little or no light-emitting matter, dominated instead by unseen forces and dark regions whose properties you can only infer. Ultimately, the large-scale structures of the universe emphasize the contrast between visibility and reality. You perceive islands of matter, galaxies, clusters, filaments, embedded within a much larger and largely empty expanse. The cosmos is a lattice of the seen and unseen, a network of luminous traces suspended in a vast, dark void. The universe you map is orderly, but its order depends on forces and matter that remain largely invisible, leaving most of reality unobserved and unknowable. Cosmic voids and the silence. Between the spaces between filaments and clusters are vast, almost empty. You might assume emptiness is trivial, but these voids dominate volume. They are real and measurable by their lack of matter and light. Yet most of the universe resides here, beyond your direct perception, forming a silent architecture that shapes everything you can see. When you map the large-scale structure of the universe, the filaments and walls of galaxies appear prominent, stretching across hundreds of millions of light years. But these luminous structures occupy only a small fraction of space. The rest is dominated by voids, immense regions where galaxies are sparse, but is diffuse, and light barely exists. These voids are not a mere absence. They are vast, coherent structures with measurable boundaries and properties. They form the background against which all visible structures are arrayed, defining the skeleton of the cosmos in silence. You might assume that empty space is inert, that it is a passive stage on which galaxies perform their motions. Observations reveal the opposite. The distribution of voids influences the dynamics of surrounding structures. Galaxies at the edges of voids experience gravitational effects, subtly accelerating along filaments or being drawn toward clusters. Even the motion of superclusters and the shape of filaments respond to the contours of these empty regions. The voids, though largely invisible, are active participants in the organization of the cosmos, dictating motion without being seen. Voids also carry a subtle imprint of the early universe. Their size and distribution encode the growth of primordial density fluctuations, the same variations observed in the cosmic microwave background. You can measure the expansion of voids over cosmic time, the way their interiors become emptier as matter flows toward surrounding filaments. These measurements allow you to test models of cosmology, but always indirectly. You detect voids by what is missing, by absence, by silence, by the gravitational influence on structures that are visible. The vast majority of the universe resides in these spaces, but your experience of it is mediated entirely by what surrounds it. The scale of cosmic voids is staggering. Some span hundreds of millions of light years, dwarfing any cluster of galaxies. Within these regions, the density of ordinary matter is less than 10% of the cosmic average. You are looking at regions of near total emptiness, where light is scarce and interactions between matter are infrequent. Yet, in this emptiness lies the majority of volume. Most of the universe is silent, unlit and unobserved, existing in a form that is both pervasive and fundamentally inaccessible. Even theoretical models underscore the dominance of voids. Simulations of cosmic evolution show that voids occupy the largest fraction of space, expanding as matter condenses into filaments and clusters. The universe is a lattice of presence and absence, of visible structures embedded within vast, silent regions. Your measurements of matter and light reveal only the tip of this iceberg. The bulk of the cosmos is unlit and unmeasured, its properties inferred entirely from the subtle effects it imposes on luminous matter. These voids force a re-evaluation of perception and scale. The universe is overwhelmingly empty, yet this emptiness is not uniform. It has structure, dynamics, and influence. The silent spaces between filaments are as significant as the filaments themselves, controlling motion, shaping evolution, and defining the framework within which galaxies form and evolve. You can measure their effects, yet direct observation is impossible. The majority of reality resides here, beyond sight, beyond touch, beyond conventional interaction. Ultimately, cosmic voids reveal a universe in which absence is dominant. What you perceive, the clusters, the galaxies, the stars, is only a fraction of the whole. The silent architecture of emptiness shapes the cosmos on the largest scales, defining motion, structure, and evolution. The universe is mostly void, and what you see is an ephemeral pattern suspended within vast, unobservable silence. Most of reality lies in these regions, invisible and unknowable, yet essential to the very existence of the structures you can measure. Gravitational lensing reveals the unseen light bends around mass. Through gravitational lensing, you can detect invisible structures, maps of mass not otherwise observable. What you measure is distortion, an indirect signature of reality. This reveals that most of what exists is perceptible only because it warps the space around it, never through its own emission or reflection. Einstein's theory of general relativity predicts that mass curves space-time, and that light follows these curves. When a massive object lies between you and a distant source of light, the light bends, forming arcs, rings, or multiple images. You are not seeing the object directly. You are observing the effect of its gravity on the path of photons. This phenomenon transforms your perception of the universe. Light becomes a tool to map invisible mass, revealing structures that emit no light, interact weakly with ordinary matter, and remain otherwise undetectable. Gravitational lensing is not rare. It occurs at multiple scales. Strong lensing, where images are visibly distorted or multiplied, occurs around massive galaxy clusters. Weak lensing, subtle shifts in the apparent shapes of distant galaxies, occurs across the sky, revealing the pervasive distribution of mass on cosmological scales. Through these distortions, you can map dark matter, which neither absorbs nor emits light, but dominates gravitational influence. The majority of the universe's mass is visible to you only because of the way it bends light, making the unseen temporarily perceptible. Clusters of galaxies provide striking examples. The luminous galaxies form only a fraction of the total mass. By observing lensing effects, you can construct a map of the dark matter halo encompassing the cluster. You see that most of the mass is invisible, distributed around and between the galaxies. Yet it determines the motions of the visible components. Light becomes a probe, a means to perceive the imperceptible. Without lensing, the vast majority of the cluster's structure would remain completely hidden. Even in regions devoid of visible galaxies, lensing reveals hidden mass. Filaments of dark matter, connecting clusters, can be mapped through their subtle influence on background light. You measure distortions in thousands or millions of distant galaxies to detect these structures. These filaments are invisible in every traditional sense, yet their presence is undeniable. You are observing reality indirectly, perceiving mass through its effect on space-time rather than through light itself. Gravitational lensing also emphasizes the fragility of observation. You cannot see matter directly. You see only its influence. Light itself is a mediator, bending along invisible contours. In a sense, the universe communicates with you, not through direct signals, but through distortions and deflections. Most of what exists, the scaffolding of dark matter, the invisible filaments, the halos around clusters, remains unseen, perceptible only because it warps the space in which light travels. Your view of reality is filtered, partial, and fundamentally indirect. The scale of these unseen structures is staggering. Filaments stretch across hundreds of millions of light years, connecting clusters across vast voids. These are the conduits of matter and gravity, shaping the growth and motion of everything you can detect. Yet they remain invisible to every sense and instrument that depends on electromagnetic radiation. Only through lensing do they become detectable, and even then, only as distortions, shadows of their true presence. Ultimately, gravitational lensing demonstrates a profound truth. The universe is mostly hidden. Ordinary matter is a trace embedded within a far larger, invisible framework. What you can see, galaxies, clusters, light from distant stars, is subordinate to mass that never emits, reflects, or absorbs light. The cosmos you perceive is defined as much by its unseen components as by the luminous ones. Most of reality exists in shadow, perceptible only because it bends the paths of light around it, revealing that what is unseen is, in fact, the dominant structure of everything you can observe. The universe's expansion is not uniform. Redshift shows the universe is expanding, but this expansion is not smooth. Galaxies move with peculiar velocities, clusters pull unevenly, filaments twist. Observations contradict the idea of a calm, uniform cosmos. Even as light reaches you from great distances, it carries the imprint of invisible forces shaping the void. The Hubble law describes a simple principle. Galaxies recede from each other at speeds proportional to their distance. At first glance, this suggests a uniform stretching of space. Yet careful measurements reveal deviations from this idealized motion. Galaxies have peculiar velocities, motions relative to the general expansion. These deviations are small compared to cosmic scales, but measurable and significant. They reveal the gravitational influence of structures, both visible and invisible. Clusters of galaxies exert massive local forces. Galaxies are not only carried outward by expansion, but also tugged toward concentrations of mass. Filaments of dark matter act like invisible highways along which matter flows. You observe galaxies being accelerated, decelerated, or deflected in ways that cannot be explained by visible mass alone. Their light, traveling across billions of light years, arrives altered not only by distance, but by the gravitational contours it has traversed. The universe is dynamic, restless, and uneven, far from a smooth expansion. Even vast voids influence motion. Though largely empty, their underdensity exerts a subtle effect on the surrounding structures. Galaxies near the edges of voids accelerate outward, flowing along filaments or toward clusters, as if the absence of matter itself has a directional influence. The expansion you measure is shaped by both presence and absence, by mass and by void. Space is stretched unevenly, sculpted by invisible structures that dominate the gravitational landscape. Redshift surveys make this visible. Maps of the local universe show large-scale flows, coherent motions, extending across hundreds of millions of light years. The Great Attractor is one example, a region toward which galaxies in the surrounding volume appear to be moving. its mass inferred indirectly through motion rather than direct observation. Such anomalies demonstrate that expansion is not isotropic. It is threaded by the invisible, shaped by forces beyond ordinary perception. What you detect in light is a combination of recession and gravitational influence, an imprint of the unseen universe. This uneven expansion also affects your understanding of cosmology. Simple models assume uniformity for convenience, but reality is layered. Space stretches, galaxies move, and light carries information about the hidden structures that impose these motions. Observing distant supernovae or measuring the cosmic microwave background reveals slight anisotropies, variations in density, gravitational potential, and flow that testify to an underlying inhomogeneity. Expansion is not a tranquil, uniform unfolding, but a process modulated by mass, void, and dark matter scaffolding. Even light itself bears witness. Photons from distant galaxies arrive redshifted not only by the expansion of space, but also by gravitational effects along the line of sight. They are subtly altered in energy and trajectory by dark matter, filaments, and unseen clusters. What reaches you is a distorted signal, carrying encoded information about invisible influences. You measure recession, but embedded within it is a record of structure, of motion, of forces acting across distances far greater than any human-scale comprehension. The uneven expansion emphasizes the universe's subtle complexity. Space is not a passive stage. It is a medium shaped by mass, energy, and absence. Filaments twist, voids shape, flow, and clusters tug in directions that betray the presence of unobservable matter. What appears as a smooth expansion is a layered, textured process, controlled by the gravitational framework of the unseen. Your observations are only partial, capturing both the uniformity of Hubble's law and the deviations imposed by invisible structures. Ultimately, the non-uniformity of cosmic expansion underscores the disconnect between perception and reality. You can measure redshift, calculate distances, and map motion, yet the majority of the forces at work remain hidden. Light reaches you altered, carrying a subtle record of a universe dominated by unseen mass and void. Expansion is not a simple stretching of space, but a dynamic interplay of observable and imperceptible components. The universe is far more restless, structured, and unknowable than any uniform model might suggest, and the motions you measure are shaped by the invisible majority of reality. Neutrinos, ghost particles, everywhere. Billions of neutrinos pass through you every second. They interact so weakly that you are entirely unaware of them. Yet, They are relics of the earliest seconds of the universe, permeating space far beyond the limits of visible matter. The universe is filled with these unseen particles, an invisible backdrop to everything you measure. Neutrinos are fundamentally different from the matter you experience. They carry mass, but it is minuscule, almost negligible compared to protons or electrons. They do not emit or absorb light, do not interact electromagnetically, and pass through ordinary matter as if it were almost entirely transparent. Every object around you, every planet, star, and galaxy, is essentially invisible to these particles. Yet, their sheer abundance makes them a significant component of the universe, a silent sea flowing through every cubic centimeter of space. These ghostly particles are not new. They have existed since the first second after the Big Bang, when the universe was a hot, dense plasma of elementary particles. As the universe cooled and expanded, neutrinos decoupled from other matter, streaming freely across the cosmos. What you detect today is not produced locally, but is a fossil from the earliest epoch, carrying a record of conditions that you cannot access through light or electromagnetic signals. In a sense, they are a direct connection to a universe you cannot see. Neutrinos also exist in layers. There are those produced in the early universe, cosmic neutrinos filling space uniformly, and those produced continuously in stars, supernova, and other high-energy events. The flux passing through you is vast. Billions of neutrinos from the sun alone intersect every square centimeter of your body each second. Yet these interactions are so weak that the vast majority pass unimpeded, leaving no trace. You coexist with an entire population of particles that are real, pervasive, and physically influential, but entirely imperceptible without sophisticated detectors. Detection is difficult. Only massive underground detectors, filled with water or ice, can occasionally observe a neutrino. By the rare instances it interacts with atomic nuclei. Even with such instruments, events are sparse and indirect. The vast majority of the neutrino background remains beyond reach, invisible not due to distance, but because of fundamental properties of interaction. You are surrounded by matter that cannot be observed through conventional means, an omnipresent yet almost entirely inaccessible component of reality. Neutrinos also influence the evolution of the universe. Despite their low mass, their abundance contributes to the overall energy density of the cosmos. They affect the formation of large-scale structures, subtly altering the growth of filaments, clusters, and voids. Models of cosmic evolution must account for their presence, yet their effects are mediated only through gravity or rare collisions. You measure their influence indirectly, reconstructing their role from motions and distributions of visible matter. The universe, once again, demonstrates that the majority of its content is unseen. Even more striking, neutrinos illustrate the multiplicity of invisible components. Alongside dark matter, dark energy, and cosmic voids, neutrinos form a pervasive background that is real, yet imperceptible. They are particles that have always existed, flowing through space silently, unaffected by stars, planets, or observers. Every cubic centimeter of the universe is saturated with them. You move through billions each second, yet their presence is known only through calculation, inference, and the rare indirect detection events. Ultimately, neutrinos reinforce a quiet but profound conclusion. The cosmos is overwhelmingly filled with imperceptible constituents. What you can see, the stars, galaxies, gas, and dust, is a minority of the total matter and energy. The universe is largely composed of elements you cannot perceive. Dark energy pushing space outward, dark matter sculpting structure, and neutrinos flowing endlessly through the void. Reality, as you measure it, is embedded within a vast, invisible framework, and most of it remains forever beyond ordinary detection. The universe is alive with ghostly matter, and your perception accounts for only a small, luminous fraction of what truly exists. The limitations of light. You measure the universe almost entirely through photons, yet photons reveal only a fraction of reality. Many processes are invisible, leaving traces only in gravitational shifts or particle interactions. Light is your main tool, but it is blind to most of existence, producing an incomplete and misleading map of the cosmos. Every observation you make relies on photons. From the glow of nearby stars to the faint microwave background from the early universe. You infer distance, composition, temperature, and motion from these particles. They are your primary conduit to the cosmos, your window onto space and time. Yet this window is narrow, selective, and biased. Light only interacts with certain types of matter. It cannot reveal the dark scaffolding of galaxies, the silent flow of neutrinos, or the pervasive influence of dark energy. Most of the universe is fundamentally invisible to it. Even luminous matter tells an incomplete story. Galaxies, gas clouds, and stars are the sources of the photons you detect, but they comprise only a small fraction of mass and energy. The majority of cosmic mass is hidden in dark matter, which emits no light, absorbs none, and reflects nothing. Its presence is revealed only indirectly through gravitational lensing, rotation curves, and large-scale structure formation. Photons provide no direct interaction with it, leaving your measurements inherently partial and dependent on inference. Light also carries a delay. It travels at a finite speed, so every observation is a look into the past. The photons arriving from distant galaxies or cosmic backgrounds represent states billions of years old, frozen at the moment they were emitted. You perceive a universe that existed long before the present, yet the regions beyond your observational horizon remain inaccessible. Even the photons you detect cannot bridge the gaps imposed by distance and time. What you see is a fraction of a fraction, constrained by both physics and history. Some phenomena are entirely invisible to light. High-energy neutrinos, cosmic rays, and gravitational waves pass through matter without producing photons. Their detection requires specialized instruments, separate from optical or radio telescopes. Even within electromagnetic observation, dust and gas can obscure light, absorbing or scattering photons and hiding structures behind layers of opacity. Your instruments capture only what escapes, leaving massive volumes unilluminated. The map of the universe you construct from photons is, by necessity, incomplete. Moreover, light is influenced by the medium it traverses. Gravitational lensing bends paths, redshift stretches wavelengths, and scattering modifies intensity. Every photon is altered by the journey, carrying subtle imprints of unseen structures and forces. What you measure is not a pure signal from a source, but a convolution of light and the intervening universe. Even the luminous universe is distorted, filtered through invisible matter and energy that shape its arrival at your instruments. The limitations of light extend to scale and context. Bright objects dominate your perception, while dim structures, diffuse matter, and background radiation are easily overlooked. Vast regions of the universe are filled with matter that interacts weakly or not at all with photons, leaving them uncharted and unobservable. The apparent distribution of galaxies, clusters, and filaments is only the luminous skeleton of a far larger, hidden framework. Light exposes some of reality, while concealing the majority, producing a perception that is simultaneously accurate and profoundly incomplete. Ultimately, photons constrain not just what you can see, but what you can know. Your instruments translate light into information, yet the universe communicates through more than electromagnetic radiation. Gravity, particle fluxes, and space-time curvature carry messages that photons cannot convey. Reality is dominated by components invisible to your main observational tools. And the universe you reconstruct from light is only a partial, filtered shadow of the whole. Light illuminates, but it also deceives, revealing a cosmos whose true extent, composition, and dynamics remain largely hidden from view. The universe is mostly empty. Even where matter exists, it is sparse. Average density is so low that space is, for all practical purposes, a vacuum. You assume the cosmos is filled with stars and gas, but your perception is dominated by rare concentrations. Most of the universe is inaccessible, not through distance alone, but through absence, a scarcity that defines its structure. When you measure the mass of the cosmos, the numbers are startling. The density of ordinary matter, protons, neutrons, electrons, averages only a few atoms per cubic meter. This is less than the emptiest laboratory vacuum you could create on Earth. Galaxies and clusters are islands of matter suspended in vast seas of emptiness. Even within these concentrations, much of the volume is interstellar or intergalactic space, almost entirely devoid of particles. Your intuitive sense of a filled universe is misleading. The cosmos is overwhelmingly empty. The emptiness is not uniform, yet it dominates. Filaments of galaxies trace out structures, but they occupy a tiny fraction of the total volume. Between these filaments lie cosmic voids, regions hundreds of millions of light years across, where matter is exceedingly rare. These voids contain fewer than 1/10 the average density of the universe, yet they constitute the majority of space. The universe's structure is defined more by absence than presence, with matter clustered sparsely along an invisible scaffolding of gravity. Even the brightest stars occupy negligible volume. The sun, though enormous by human standards, is microscopic in the context of cosmic scales. Its photons traverse vast expanses before encountering another particle. Galaxies, though containing billions of stars, are mostly empty space between them. What you see as a crowded cosmos is, in reality, a landscape dominated by near total emptiness. Your instruments detect the rare islands of matter, but they reveal little about the vast voids that constitute most of the universe. This scarcity shapes motion and evolution. Galaxies move along filaments, accelerating toward clusters or flowing around voids. The dynamics of the universe are dictated not only by concentrations of matter, but by the emptiness that surrounds them. The vacuum is not inert. It is the medium through which forces propagate, the space in which light travels, and gravitational influences extend. Even the absence of matter has consequences, shaping the formation and distribution of the visible universe. Cosmic expansion amplifies emptiness over time. As space stretches, regions already sparse become sparser, pushing galaxies and clusters further apart. The observable universe is shrinking in practical terms. Distant structures recede faster than light can reach you, leaving increasingly isolated pockets of matter amid an ever-growing void. What you can detect will diminish over billions of years, leaving a universe even more dominated by emptiness, where your measurements reflect only remnants of an otherwise inaccessible cosmos. The low density also exposes the limitations of observation. Light travels across near-perfect vacuums, but the majority of matter it could interact with is absent. Photons encounter fewer obstacles, yet the sparse interactions reveal only small fractions of the total structure. Dark matter, which dominates the gravitational framework, is also distributed primarily in the empty regions, influencing motion silently, without light, without detection, and without direct interaction. The emptiness conceals most of reality from direct measurement. Ultimately, the universe's vast emptiness reframes your understanding of existence. What you perceive, the stark galaxies, clusters, is the exception, not the rule. The cosmos is dominated by absence, by voids, and near-empty space, by regions whose properties you infer indirectly. Most of what exists lies in nothingness, inaccessible to light, touch, or conventional observation. The universe is a lattice of rare presence embedded within overwhelming emptiness, and your perception captures only a thin, illuminated fraction of a far larger, mostly empty reality. The horizon problem. Regions of space that could never have been in contact exhibit almost identical properties. The uniformity of the cosmic microwave background suggests coordination beyond causal reach. You observe similarity without explanation, a subtle contradiction embedded in the fabric of space-time itself. When you measure the temperature of the cosmic microwave background, you find that it is the same across vast swaths of the sky, varying by only 1 part in 100,000. This uniformity is striking because light, and with it information, could not have traveled between the most distant regions within the age of the universe. At the time the radiation was emitted, regions separated by hundreds of millions of light years could not have influenced each other. Yet they share almost identical temperatures and densities. The horizon problem highlights a fundamental limit in causal connection. Signals cannot travel faster than light, so any region beyond another region's horizon is, in principle, causally disconnected. Despite this, the early universe exhibits coherence. Measurements of density, fluctuations and anisotropies in the CMB reveal patterns that are remarkably similar across distances that should have been isolated. This is not a minor anomaly. It is a discrepancy rooted in the basic assumptions of space, time, and the propagation of information. Attempts to explain this uniformity lead to counterintuitive conclusions. Inflationary theory proposes that the universe underwent a brief period of exponential expansion, stretching a tiny, causally connected region to encompass the observable cosmos. While this accounts mathematically for the uniformity, it implies that almost all of the universe we see originated from a minuscule patch, smaller than any current observational scale. The consequence is that what you measure is a magnified image of an originally tiny and homogeneous region, surrounded by regions that remain forever beyond reach. Most of the universe remains causally disconnected, yet the visible fraction appears coordinated as if it were not. Even with inflation, the horizon problem introduces unease about scale and observation. You measure a universe that seems coordinated over distances that cannot physically communicate. Light carries information from the past, yet the initial conditions encoded in that light suggest a level of uniformity that should be impossible. You are observing a cosmos whose largest structures and earliest moments defy simple causal explanation, forcing a reconsideration of what it means for events to be connected in space and time. The problem extends beyond temperature. The distribution of matter, the formation of galaxies, and the clustering of large-scale structures all reflect initial conditions encoded in these early moments. Yet these conditions span regions that were never in contact. The observable universe presents a coherent, interconnected image, while the vast majority of space outside this horizon remains unseen and potentially uncoordinated. You are forced to reconcile the apparent unity of what is observable with the disconnect of what cannot be observed. The horizon problem also emphasizes the incompleteness of measurement. You can map the CMB, trace structures, and calculate expansion, but the vast regions beyond the horizon are inaccessible. Their properties are unknown, and yet they may differ in ways you cannot detect. Uniformity within your observable bubble may be a local phenomenon, not a universal one. Reality extends beyond the reach of light and causality, leaving most of the cosmos forever unknown. Ultimately, the horizon problem reveals a subtle tension between observation and theory, between what can be measured and what is physically possible. You see a universe coordinated across regions that could never have communicated, an ordered imprint frozen into the earliest light. The contradiction is real, rooted in observation and physical law. The universe you perceive is coherent, but only a small fraction of the whole. Beyond the horizon lies an expanse where uniformity cannot be assumed, where the properties of space-time may differ, and where the majority of reality remains inaccessible to all observation. Inflation and the unseen expanse. The early universe underwent exponential inflation, stretching regions beyond your observable horizon. There exist areas whose light will never reach you. You can calculate their existence, predict their influence on large-scale structure, but they remain permanently invisible, a consequence of processes far beyond human timescales. Inflation is theorized to have occurred within a fraction of a second after the Big Bang. During this period, space expanded exponentially, far faster than the speed of light, stretching microscopic regions to scales billions of times larger. The regions that were once in causal contact were suddenly separated, leaving vast volumes of space forever outside each other's horizon. You can infer this process from the uniformity of the cosmic microwave background, from the spectrum of density fluctuations, and from the large-scale distribution of matter. Yet the regions themselves remain inaccessible, their properties beyond direct observation. What you measure today is a small bubble within a far larger cosmos. Beyond the edge of your observable universe, inflation implies the existence of countless other regions, potentially infinite in number. Each of these regions could contain matter, radiation, and structure, but no light from them will ever reach you. Their influence is subtle, encoded indirectly in the large-scale gravitational distribution you can observe, yet the majority of their content remains hidden. You perceive their existence mathematically, not empirically, a universe inferred rather than seen. The implications are profound. Inflation produces a cosmos where your observable horizon is a tiny fraction of the whole. Structures you detect, the filaments, clusters, and walls of galaxies, may be repeated, modified, or entirely absent in regions beyond. The coherence you observe in the cosmic microwave background does not extend globally. Your measurements reveal a connected patch, but most of reality lies outside this patch, unobservable, untouched, and unknown. Even the light you do receive is a product of this expansion. Photons from distant galaxies and the early universe have traveled vast distances through a space that has itself stretched enormously. What arrives at your instruments is delayed, altered, and filtered by the expansion of space-time itself. You observe a universe in which time, distance, and scale are warped by processes that occurred before stars, galaxies, or even atoms existed. Light provides information, but only within a narrow horizon. leaving the vast majority of the cosmos perpetually unseen. Inflation also shapes the distribution of matter and energy on the largest scales. Regions expanded differently. Quantum fluctuations during inflation seeded the density variations that later grew into galaxies and clusters. Yet the majority of these variations and the structures they produced occur outside your observational reach. You detect only a subset of the total patterns, a small, luminous fraction of a far more extensive cosmic network. Most of the universe remains a silent, unlit expanse, its existence inferred through mathematical necessity rather than direct observation. This unseen expanse is permanent. The limits imposed by light, travel, and expansion ensure that the regions beyond your horizon will never interact with you. They are a consequence of the universe's earliest processes, beyond the scope of any measurement you can perform. Gravity, light, and time all conspire to isolate these regions, making your observable universe a finite island within a vast, possibly infinite, ocean of space. Ultimately, inflation reveals a cosmos in which most of reality is forever inaccessible. You can calculate the existence of regions you will never see, predict their gravitational influence, and model their effects on cosmic structure. Yet the majority of space lies silent, unobserved, and unobservable, stretched beyond the reach of light or causal contact. The universe you inhabit is only a fraction of what exists, a tiny illuminated bubble suspended within a vast, unseen expanse whose scale and properties are largely beyond your comprehension. The multitude of unobservable galaxies. Simulations suggest countless galaxies lie beyond your horizon. Each is as real as the Milky Way, yet forever inaccessible. Your instruments cannot touch them. Your light cannot reach them. The universe you measure is a thin slice of a far larger, unknowable expanse. The observable universe is limited by the speed of light and the age of the cosmos. Photons from regions beyond roughly 46 billion light-years have not had time to reach you. Yet cosmological models, grounded in inflation and the distribution of matter, predict that galaxies exist far beyond this horizon. Their light will never arrive, and no causal influence they exert can ever affect your region. You are confined to a fraction of the total cosmic volume, a luminous bubble in an otherwise infinite or near infinite expanse. These galaxies, though unobservable, are expected to be similar to those you can see. They likely contain planets, and gas, arranged in familiar structures. Yet you will never confirm their existence empirically. all knowledge of them is indirect, derived from mathematical models and simulations based on the physics of the universe. Gravity, cosmic expansion, and the growth of structure predict their presence, but you can never place a telescope in their direction and measure their light. They remain permanently beyond your reach, real only in calculation and inference. The scale is staggering. While the observable universe contains hundreds of billions of galaxies, simulations suggest that this is only a tiny fraction of the total. Each of these unobservable galaxies is itself a vast system, potentially containing billions of stars, planets, and other structures. Multiply these numbers across the entirety of space, and you confront a reality so immense that your perception, instruments, and comprehension capture only an infinitesimal part. What you see is a minor fraction of the totality, a slice defined by the finite speed of light and the constraints of observation. Even within this limitation, the invisible galaxies exert influence. Their mass contributes to the overall curvature and dynamics of space-time, affecting gravitational waves, large-scale structure, and the motion of clusters indirectly. You measure some of these effects, but the sources are entirely out of reach. Their presence is inferred, not observed. The universe you can interact with is a subset defined not by absence of existence, but by absence of light and causal connection. The horizon also imposes a permanent boundary. As the universe continues to expand, more galaxies will cross beyond the observable limit. Today's visible galaxies may become tomorrow's unreachable islands, carried away by accelerated expansion and dark energy. The proportion of the cosmos accessible to observation will shrink over time, leaving an even thinner slice of measurable reality. The majority of galaxies already unseen will never enter view. Your perception of the universe is transient and incomplete, a snapshot confined to a particular horizon. These unobservable galaxies reinforce a fundamental asymmetry. You can measure, catalog, and study structures within your horizon, but their existence is a local phenomenon. Beyond your reach, the universe may continue indefinitely, filled with systems as real and complex as those you can observe. The cosmos you map is not representative of the whole. It is a small, illuminated region, embedded within a far larger, permanently inaccessible expanse. Ultimately, the multitude of unobservable galaxies emphasizes a stark truth. Reality is vastly more extensive than perception allows. Every observation, every instrument, and every photon you measure reveals only a fraction of the universe. Beyond the horizon lies a sprawling, unmeasured domain filled with galaxies, stars, and structure that will never touch your instruments or reach your eyes. The universe you inhabit is a thin slice of the whole, a limited view of a cosmos whose full scale is unknowable, and whose majority exists beyond both light and causal connection. Black holes as cosmic voids. Black holes hide information. Matter collapses. Light cannot escape, yet their gravity shapes galaxies and clusters. These objects are fundamentally unseeable except through indirect influence. The universe is threaded with these unseen points of consequence, punctuating space with hidden reality. A black hole forms when matter is compressed beyond a critical threshold, creating a region where gravity overwhelms all other forces. The event horizon marks a boundary from which no light, no particle, and no information can return. You cannot observe what lies within. All you can measure is the effect of the black hole on its surroundings, the orbit of stars, the motion of gas, the bending of light. These measurements reveal the presence of the black hole, but never the interior. Its reality is inferred entirely from influence, a consequence without direct observation. Supermassive black holes occupy the centers of most galaxies, including your own Milky Way. Their masses are millions or billions of times that of the Sun, yet they occupy a volume smaller than the solar system. Despite their invisibility, they govern the dynamics of surrounding stars, regulate the flow of gas, and influence the formation of galactic structure. You see the galaxies themselves, but at the heart of each is an object that is fundamentally hidden, shaping the cosmos in silence. Stellar mass black holes are far more numerous, formed from the deaths of massive stars. They drift through galaxies largely unnoticed, detectable only when interacting with nearby matter. Many float isolated in space, invisible to all methods of direct observation. Your instruments are blind to the vast majority of these objects. You measure their existence indirectly, through gravitational perturbations or rare bursts of radiation from accretion events. The universe is populated with these hidden entities, a background of mass that is imperceptible except through its consequences. Even light itself is altered by black holes. Gravitational lensing around these dense regions bends the trajectory of photons passing nearby, producing arcs and distortions in distant images. You can map mass distributions, infer the presence of invisible objects, and measure the warping of space. Yet the black hole interior remains inaccessible, a singularity cloaked in unmeasurable conditions. Information, as it enters the horizon, is lost from any observational perspective. The cosmos contains volumes that are physically real, yet permanently unknowable. Black holes also reveal the limits of knowledge in time. Matter that falls within is trapped forever, unreachable even by the expansion of the universe. Signals from inside cannot propagate, leaving an information gap. The processes within the event horizon are inaccessible, not because of distance, but because of fundamental physical constraints. Each black hole is a void of information, a locus where certainty ends and only inference remains. The distribution of black holes punctuates the universe with points of hidden reality. Their gravitational influence organizes galaxies and clusters, shapes star formation, and affects cosmic evolution. Yet the majority of their mass and content remains forever unseen. They exemplify a principle seen repeatedly in cosmology. Much of reality exists not for direct observation, but for indirect measurement, for inference, for its consequences on the visible universe. Ultimately, black holes emphasize that the universe is threaded with inaccessible structure. You can measure the effects of mass, light, and motion, but the objects themselves remain fundamentally hidden. The cosmos is not only filled with empty voids and invisible galaxies, but also punctuated by singularities where information and observation cease. Reality is layered, and your perception captures only the luminous and accessible fraction. The majority of cosmic influence occurs in silence, in regions that can never be seen, only felt through their gravitational imprint on the visible universe. The cosmic web's invisible threads, intergalactic filaments, contain gas and dark matter, mostly undetectable. You infer their presence through the motion of galaxies or faint absorption lines. Vast highways of matter connect clusters across incomprehensible distances. Yet these threads are invisible to the naked eye, silently structuring the cosmos. The large-scale structure of the universe is dominated by these filaments, forming a web that stretches across hundreds of millions of light years. Galaxies are not distributed randomly. They trace the contours of this hidden framework, flowing along dense strands and clustering at intersections. The filaments themselves are mostly composed of dark matter, a substance that does not emit, absorb, or scatter light. Ordinary matter, gas and dust, occupies only a fraction of the volume. What you perceive as isolated galaxies is actually part of a vast, interconnected network, largely invisible except for its gravitational imprint. Detection relies on subtle effects. The motion of galaxies within clusters and along filaments betrays the underlying distribution of dark matter. Light from distant quasars is partially absorbed by tenuous gas in these filaments, producing faint spectral lines that reveal their presence. Gravitational lensing of background galaxies allows mapping of mass concentrations along filamentary structures. You do not see the filaments directly. You reconstruct them through their influence on light and matter. The universe communicates through distortion, motion, and absorption, not through illumination. These threads are immense. Some filaments span hundreds of millions of light years, connecting multiple galaxy clusters and forming the backbone of cosmic structure. The majority of the volume within the universe lies in voids between these threads, amplifying their significance. Though invisible, filaments dictate the paths along which galaxies form, collide, and evolve. They guide the flow of matter, channeling gas and dark matter into clusters and determining the growth of large-scale structure. You measure their influence, yet the filaments themselves remain largely beyond observation. The invisibility of the cosmic web highlights the contrast between presence and perception. Galaxies and clusters are luminous, easily measured, and mapped. Filaments, however, dominate mass distribution but evade direct detection. Most of what structures the universe is hidden, perceptible only because it affects what you can see. Your understanding of the cosmos is constructed from these indirect signals, revealing an architecture that is largely inaccessible to ordinary observation. Even the ordinary matter in filaments is sparse. Gas between clusters has extremely low density, typically a few atoms per cubic meter. This diffuse medium emits very faint radiation, often in the X-ray or ultraviolet, barely detectable across cosmic distances. The majority of intergalactic matter is effectively invisible. Its presence is inferred not through direct observation, but through absorption, gravitational influence, and simulation. The universe is organized on a scale you cannot directly apprehend, with invisible threads shaping the visible landscape. Filaments also reveal the universe's dynamic nature. Matter flows along them, feeding clusters and driving the formation of new galaxies. Streams of gas and dark matter accelerate toward gravitational wells, shaping the evolution of structures over billions of years. The unseen pathways dictate motion, mass accumulation, and eventual collapse, yet the vast majority of these highways remain imperceptible, connecting regions you may never observe. Ultimately, the cosmic web demonstrates that the universe is structured by invisible frameworks. Luminous objects mark only a fraction of the underlying order, while dark matter and diffuse gas silently define its architecture. Your instruments detect only shadows, distortions, and flows, leaving the majority of the cosmic network hidden. Reality is far more extensive, interconnected, and inaccessible than perception allows. The universe you see is embedded within an invisible lattice, and the threads of matter that shape its evolution remain unseen, silently imposing order across incomprehensible distances. The universe beyond detection. You measure, you observe, you map, but all tools have limits. There are regions where no signal can reach you, no particle can travel, no influence is detectable. These zones exist physically, but are epistemically absent, forming a shadow domain that science can only describe through absence. The boundary of observation is defined by the finite speed of light and the age of the universe. Photons from beyond roughly 46 billion light-years have not yet reached you. No matter how powerful your instruments, no matter how sensitive your detectors, these regions remain permanently inaccessible. They exist, you calculate, yet they leave no direct trace. Your knowledge of them is necessarily indirect, derived only from theory, simulation, and the inferred effects of processes within the observable patch. These invisible regions are not empty in a theoretical sense. Simulations based on inflation, dark matter distribution, and cosmic expansion predict vast numbers of galaxies, clusters, and filaments beyond the horizon. Yet you will never see them, interact with them, or measure them. Their light is forever beyond reach, and any gravitational influence they exert on observable matter is negligible due to distance and accelerated expansion. They are physically real, yet they occupy a domain that is epistemically empty, realities that science acknowledges but cannot access. Even massive structures, when located in these unobservable regions, remain hidden. You can model their formation and infer their existence through cosmological principles, yet they remain as unreachable as stars on the far side of the universe. Dark matter, dark energy, and intergalactic filaments extend beyond the observational horizon. These invisible networks shape the dynamics and evolution of the cosmos you can see, yet their most distant reaches remain unmeasured. The universe is larger than your instruments, larger than light itself, and larger than the observational frameworks that define scientific certainty. This shadow domain also challenges your assumptions about uniformity. You observe isotropy within your horizon, yet there is no guarantee that the universe beyond is similarly structured. Inflation predicts vast regions beyond your reach, possibly with properties subtly or radically different from what you can detect. The observable universe is a small, coherent bubble within a potentially infinite, largely unobservable expanse. Reality extends far beyond what light, matter, or causality can carry to you. The limits are not merely spatial, but causal. Signals cannot propagate faster than light, and the accelerated expansion of space ensures that distant regions will recede faster than light can bridge the gap. Even gravitational influence is confined by these horizons. The unseen domains exert little to no measurable effect on your observable region. These parts of reality exist, yet they are fundamentally outside the epistemic reach of observation, forming a boundary where knowledge itself ceases. Science describes these zones only through absence. You infer their existence from the requirements of cosmological models, from the dynamics of expansion, and from the coherence of observable structures. They are a necessary consequence of the universe's history and underlying laws, yet they are undetectable by any practical means. The physical world continues beyond the reach of measurement, yet epistemically it is a void, a shadow universe whose existence is real but unobservable. Ultimately, the universe beyond detection underscores a persistent tension between presence and perception. What exists is vastly larger than what can be known. Observation, measurement, and light illuminate only a fraction of reality, leaving the remainder physically real but epistemically absent. The universe is not bounded by the limits of perception. It extends into regions you cannot access, into domains where matter, energy, and structure exist without ever communicating with you. Science can describe the necessity of these zones, predict their properties, and include them in models. Yet they remain forever beyond direct experience. Reality is therefore partially hidden, its majority existing in silence, inaccessible to light, information, and the tools by which you attempt to measure it. Entropy and the invisible future. The second law of thermodynamics ensures the universe evolves toward higher entropy. You can observe stars burning out, galaxies dispersing, but the eventual state is dominated by invisible energy, dispersed matter, and faint radiation. The majority of the universe is already moving toward unobservability, toward quiet dissolution. Stars, the luminous engines of galaxies, burn through fuel with a predictable efficiency. Hydrogen fuses into helium into heavier elements, releasing energy in the process. Light radiates outward, illuminating galaxies, clusters, and filaments. Yet this process is temporary. Each star eventually exhausts its nuclear fuel, collapsing into white dwarfs, neutron stars, or black holes. The bright matter you can observe is steadily diminishing, leaving the universe increasingly dark and diffuse. Galaxies themselves are not immune. Over billions of years, stars drift apart, interactions slow, and gravitational systems relax. Clusters may merge, while filaments thin as dust. Expansion stretches matter across incomprehensible distances. The density of observable objects declines, and the contrast between luminous structures and the surrounding void fades. Even the bright patches of the cosmos are ephemeral. You witness order, but it exists only temporarily against a backdrop of growing uniformity and entropy. Beyond stars and galaxies, entropy governs all energy. Radiation from luminous sources spreads over vast volumes, cooling as the universe expands. Photons become redshifted, their wavelengths stretched until they carry almost no energy. Light, which has been the primary tool of observation, loses its effectiveness. Gradually, the universe becomes dominated by low-energy photons and sparse matter. A landscape where the majority of physical processes occur without producing measurable signals. The cosmos moves toward a state in which observation itself is limited by entropy. Even matter itself is affected. Interstellar gas thins. Black holes slowly evaporate through Hawking radiation, and diffuse particles spread across ever-growing volumes. The majority of energy and mass becomes effectively invisible. What you can detect, the stars, the clusters, the filaments, is only a fraction of the ongoing entropy-driven evolution. Reality is gradually transitioning to a state where most constituents exist without producing observable effects. Light, heat, and structure become sparse, leaving the universe increasingly dominated by quiet, unobservable energy. This process also emphasizes the universality of entropy. It is not confined to individual stars or galaxies. It applies to the universe as a whole. The expansion of space amplifies its effects, separating structures and stretching energy across larger volumes. Gravity cannot counteract this trend indefinitely. Even the largest and most massive structures are slowly overtaken by the relentless march toward disorder. The universe is steadily progressing into a state where causal influence, observable interactions, and luminous matter are all diminished. Entropy's trajectory is irreversible. The processes that generate structure, light, and motion are fleeting in cosmic terms. The majority of the universe, whether already in voids, dark matter halos, or the distant, unobservable reaches, is moving toward a state in which its energy is dispersed and its matter diffused. The cosmos is becoming quieter, more uniform, and largely invisible to any form of direct measurement. Observation, perception, and interaction are increasingly constrained by the very laws that govern existence. Ultimately, Entropy ensures that the universe's future is dominated by the unobservable. Stars fade, galaxies disperse, light loses energy, and matter spreads thinly across expanding space. The majority of reality, matter, energy, and structure, slips into forms that cannot be seen, felt, or measured, existing only as low-density, low-energy traces. The cosmos is moving toward an invisible future, one in which the processes you rely on for knowledge are fading, leaving a quiet, diffuse, and largely inaccessible universe. What you observe now is temporary, a luminous snapshot in a broader evolution toward silence and invisibility, and the majority of cosmic existence is already slipping beyond reach. Gravitational waves and hidden events, colliding, black holes and neutron stars produce ripples in space-time. You can detect them only with extreme instruments. Vast cosmic events occur entirely without light, leaving traces only in distortions you barely perceive. The universe is active beyond vision, yet most of its activity is unseeable. When two massive objects spiral inward and merge, they release energy not in the form of light or heat, but as gravitational waves, oscillations of space-time itself. These waves propagate outward at the speed of light, compressing and stretching distances minutely as they pass. You can measure them only with instruments of extreme precision, such as LIGO and Virgo, capable of detecting changes smaller than the width of a proton across kilometers of detector arms. Even then, only the strongest, closest events register. The vast majority of such collisions across the cosmos remain undetected, imperceptible to any conventional observation. Gravitational waves reveal a universe in motion that is otherwise invisible. Black holes merge in the deep voids between galaxies. Neutron stars collide, and asymmetric supernovae ripple space-time without producing significant electromagnetic radiation. These events are fundamental to the evolution of structure, the synthesis of heavy elements, and the dynamics of mass distribution. Yet they occur largely unseen. You perceive only a fraction of this activity, and only through distortions that require sophisticated inference. The universe is far more energetic and tumultuous than your senses, or even your most sensitive instruments, can directly apprehend. Even in cases where some light is emitted, it is often negligible compared to the gravitational signal. Black hole mergers typically produce no photons, and the surrounding matter may be too sparse to generate detectable radiation. Neutron-star collisions produce bursts of gamma rays, but these are fleeting and directional. The vast majority of gravitational events produce no observable light at all. Their existence is revealed only through subtle perturbations of space-time, detectable across cosmological distances, but requiring instruments of extraordinary sensitivity. These hidden events are also widespread. Across billions of light years, countless collisions occur every year, each releasing energy beyond the capacity of any single star or galaxy. Yet most of these events leave no visible mark. They shape the universe, redistribute mass, and generate waves that traverse the cosmos without interacting with ordinary matter. Your perception of cosmic activity, dominated by photons and radiation, captures only the visible minority of what is occurring. The universe is a symphony of unseen motion, punctuated by events that you can only infer indirectly. The implications extend further. Gravitational waves propagate through regions of space entirely devoid of light, linking otherwise disconnected portions of the universe. They carry information from sources you will never observe directly, encoding details of mass, spin, and dynamics in distortions imperceptible to human senses. This information is real and measurable, yet it exists almost entirely outside the traditional framework of observation. The universe communicates through these silent distortions, revealing activity that is otherwise hidden. Ultimately, gravitational waves emphasize the limits of direct observation. The universe is not static or solely luminous. It is active in ways that largely escape detection. Collisions, mergers, and violent rearrangements occur across distances where light never reaches you. You measure only the faintest subset, reconstructing reality from minute distortions in space-time. Most cosmic events, the majority of the universe's dynamism, unfold invisibly, influencing structure, evolution, and energy distribution without ever producing a detectable signal. What you observe is a fraction of the universe's motion and transformation. Beyond photons, radiation, and direct detection lies a vast, active cosmos, with energy and matter colliding, merging, and shaping space-time silently. Gravitational waves are a window into this hidden activity. But even this window is narrow. The majority of the universe's events remain beyond perception, unseeable, and unknowable in any conventional sense. The universe is alive with unseen motion, its true activity largely inaccessible, reminding you that observation reveals only a fraction of reality, and most of what occurs is forever hidden. Cosmic acceleration hides distant galaxies. As space expands, distant galaxies move away faster than light can traverse the distance to you. These galaxies exist, but are permanently inaccessible. Their light will never reach your instruments. The universe is full, yet fundamentally invisible to your observation. The expansion of the universe is not uniform in effect. While nearby galaxies move slowly enough that light eventually reaches you, those beyond a critical distance are carried away by space itself faster than photons can close the gap. This is not a failure of light or limitation of technology. It is a consequence of the fabric of space-time expanding under the influence of dark energy. No matter how long you wait, no signal from these galaxies can arrive. They exist physically, yet remain forever outside causal connection. This cosmic acceleration ensures that the observable universe is only a small fraction of the whole. Regions that were once reachable may already be receding beyond the horizon. Galaxies that you detect today may eventually disappear from view as their recession velocity exceeds the speed at which their light can reach you. Your instruments, no matter how sensitive, are confined to a shrinking window of observation. The universe is steadily partitioning itself into islands of visibility, isolated by the very expansion that defines its large-scale structure. The effects are cumulative. As expansion continues, the number of galaxies accessible to observation will decline. Clusters will recede, filaments will stretch, and more of the cosmic web will slip beyond detection. Even the cosmic microwave background, which reveals the early universe, is a record of light emitted from a finite horizon. Beyond it lies an unobserved, unseeable expanse, growing increasingly inaccessible as dark energy drives acceleration. What you perceive today is only a fraction of what exists, and tomorrow that fraction will diminish further. Dark energy's influence also introduces asymmetry into the universe. You measure galaxies and clusters locally, yet your observations cannot confirm the properties of those beyond the horizon. Inflation predicts continuity, but you can never verify it for these distant regions. They exist mathematically in models and simulations, yet empirically, they remain absent. You live in a universe where the majority of matter is physically present, but epistemically unreachable, hidden behind an accelerating boundary. Even gravitational influence is limited. While nearby clusters tug subtly on your local neighborhood, distant galaxies carried away by accelerated expansion cannot affect you. Their mass, energy, and motion are real, yet they exert no measurable force on your instruments. The cosmos is structured beyond reach, populated by objects whose presence you can only assume, whose properties you cannot confirm, whose light will never illuminate your observations. The long-term implications are profound. Over trillions of years, the visible universe will consist almost entirely of a single bound cluster of galaxies, with the rest permanently lost beyond the horizon. The vast majority of matter, structure, and energy in the cosmos will have no causal interaction with your region. Observation, measurement, and understanding are confined to a shrinking bubble, leaving most of the universe physically real, but forever invisible. Ultimately, cosmic acceleration reveals the ephemeral nature of perception. The universe is not empty, but your ability to witness it is limited. Galaxies continue to exist beyond your horizon, yet their light and influence cannot reach you. Expansion isolates regions, partitions reality, and ensures that the majority of the cosmos is hidden from all observation. The universe is full, active, and structured, yet most of it will remain perpetually beyond the reach of human knowledge, forever inaccessible to light, gravity, or any signal you could detect. The limits of causality. You assume cause and effect link all things you observe. Yet the expansion, inflation, and horizon problems show that events beyond your horizon influence local structures without direct contact. The causal map of the universe is incomplete, leaving gaps where influence exists without trace. Causality, as you experience it, relies on signals propagating from one point to another. Light, gravity, and particle interactions define what can influence what. Yet on cosmic scales, these signals are limited by the finite speed of light and the expansion of space itself. Regions that were once in causal contact may become permanently isolated. Likewise, regions that never shared contact may nevertheless display correlations that cannot be explained through any conventional chain of cause and effect. Observations reveal uniformity and coherence, where, according to simple causal reasoning, there should be none. The cosmic microwave background illustrates this paradox. The radiation you detect today comes from regions of space that, at the time of emission, were beyond each other's horizon. Their properties, temperature, density, and composition match to remarkable precision, yet no signal could have connected them. The universe presents you with patterns that suggest coordination without causal interaction. The laws of physics remain consistent, but the framework of causality that underpins your intuition is incomplete on the largest scales. Inflation compounds the problem. In the earliest moments, space expanded exponentially, separating regions faster than light could traverse them. These regions are forever beyond each other's influence, yet they shape the overall distribution of matter, energy, and structure in ways you can measure. The gravitational potential of distant, unobservable regions affects large-scale flows of galaxies, subtly influencing motions within your local observable patch. Causality is no longer local. it becomes statistical and inferred, evident only through correlations, rather than direct interaction. Dark energy accelerates the isolation of causal domains further. As the universe expands, more regions cross beyond your horizon. Galaxies and clusters that once influenced your neighborhood through gravity will eventually recede too quickly for their effects to propagate. Even now, distant masses contribute only marginally to the local dynamics, leaving gaps in the causal map. You can observe trends, predict motion, and infer distributions. But the majority of the universe's influence occurs beyond detectable interaction. Even the concept of simultaneity becomes fragile. Events separated by vast distances are perceived in ways constrained by your own light cone. What you observe now corresponds to the past of distant regions, sometimes billions of years ago. You cannot establish a simple, universal ordering of events across the cosmos. Cause and effect, as applied locally, is clear. But when extended to unobservable regions, it loses its straightforward meaning. Influence exists without trace. Correlations emerge without transmission. And the apparent uniformity of the universe defies naive causal expectations. Quantum fluctuations during inflation introduce yet another layer of complexity. These fluctuations seeded structures billions of years later, yet the events that produced them are forever outside direct observation. The initial randomness produced coherent patterns, leading to galaxies and filaments, yet the process itself leaves no causal signature accessible to your instruments. You can reconstruct the statistical imprint, but the chain of individual causes remains hidden. Ultimately, the universe demonstrates that causality has limits. Observed structures, motions, and correlations are shaped by factors that are partially unobservable, partially inaccessible, and partially disconnected from direct interaction. You measure consequences without witnessing causes, infer patterns without observing mechanisms, and encounter regions whose influence exists only in the distortion of observable matter. The causal network of reality is incomplete, punctuated by gaps, shadowed by unobservable domains, and structured by processes that unfold beyond light, gravity, and your instruments. The universe is interconnected, yet your map of connection is fundamentally partial, leaving much of reality existing in causal silence. Matter and antimatter imbalance. The universe favors matter, yet fundamental physics predicts equal amounts of matter and antimatter. You observe a cosmos dominated by what survives, while the majority of expected matter is absent, unseen, annihilated. The imbalance reveals that the universe you perceive is a fraction of what was possible. At the moment of the Big Bang, conditions should have produced symmetric amounts of matter and antimatter. Each particle should have had a corresponding antiparticle, identical in mass, but opposite in charge. When matter and antimatter meet, they annihilate, converting mass into energy. Yet the universe today is overwhelmingly composed of matter, with very little antimatter detectable. The imbalance is not a minor discrepancy. It is a fundamental asymmetry that defines the very structure and existence of what you can observe. The evidence is everywhere, yet subtle. Cosmic rays occasionally produce antiparticles, but these are rare and isolated. Entire regions of antimatter, which should exist if symmetry held, are absent. No galaxies composed primarily of antimatter have been observed, and the boundaries between matter and antimatter, if they existed, would produce catastrophic annihilation signatures. The universe you see is therefore a survivor of selective processes, a cosmos where the vast potential of matter-energy interactions has been suppressed. This imbalance has profound implications for perception. You measure stars, galaxies, and clusters, assuming they represent the universe as a whole. Yet, they are a biased sample, the residue of a violent selection process that left only matter intact. Antimatter annihilation removed roughly half of what could have existed. The universe, in its observable form, is already a fraction, a remnant shaped by unseen processes whose consequences are embedded in the composition of every particle, every galaxy, and every photon you measure. The asymmetry is not merely a historical artifact. It shapes structure, evolution, and dynamics today. The distribution of baryonic matter, the formation of stars, and the accumulation of galaxies all reflect a universe where the bulk of antimatter was erased. The balance of mass energy you can interact with is skewed, yet the laws governing this visible portion remain consistent with fundamental physics. You perceive coherence, stability, and order. But this reality is contingent on an early universe in which half of all potential matter ceased to exist. The mechanisms behind the imbalance remain partially hidden. Baryogenesis, the process that produced excess matter, operates at energies and scales inaccessible to direct observation. The phenomena responsible are inferred from the existence of the surviving universe, not measured directly. You can model outcomes, simulate particle interactions, and apply known physical laws. Yet the actual process that tipped the balance is beyond direct observation. The majority of what was theoretically possible has left no trace other than the absence it created. Even dark matter may be influenced by similar principles. While its composition remains unknown, the invisible sector of the universe could harbor additional asymmetries, amplifying the fraction of reality that remains hidden. You detect gravitational effects, informass, and map structures, yet the underlying physical balance in these unseen components remains uncertain. Much of what structures the cosmos may itself exist as an invisible consequence of selective survival, inaccessible to direct measurement. Ultimately, the matter and antimatter imbalance emphasizes the partiality of perception. What you observe, the luminous galaxies, the stars, the gas, is a biased sample, a subset of what the universe could have been. The majority of potential mass was annihilated, leaving the surviving matter to define the cosmos you can interact with. Reality is therefore contingent, asymmetric, and incomplete. The universe you perceive is a shadow of what could have existed, its composition shaped by processes that are both fundamental and inaccessible, revealing that observation itself captures only a fraction of cosmic reality. The silence of the void. Space is not only dark, but quiet. Most interactions occur in hidden domains, mediated by invisible fields and particles. You perceive light, gravity, and occasional waves. But the vast majority of activity is undetectable, occurring beyond every measurement, every perception, every instrument. The void is not empty in a theoretical sense. It is suffused with dark matter, dark energy, neutrinos, and diffuse radiation, components that dominate mass and energy, yet escape direct observation. Most particles pass unnoticed, interacting so weakly that their presence is inferred only through indirect effects. Gravity subtly shapes motion across cosmic scales, while dark energy drives the acceleration of expansion. These invisible agents dominate dynamics, yet produce almost no detectable signals within the void. Even light, the primary messenger you rely upon, tells only a fraction of the story. Photons illuminate stars, galaxies, and gas clouds, but vast regions remain beyond reach. Intergalactic space contains matter so diffuse that emission is negligible. Gas densities are measured in mere atoms per cubic meter, insufficient to produce detectable radiation over billions of light years. The signals you do detect are punctuated by immense silence, highlighting that the observable universe is only a sparse, exceptional subset of what exists. Particles drift through this quiet expanse unnoticed. Billions of neutrinos traverse your body each second, relics of the earliest universe, yet you remain oblivious. Dark matter permeates filaments and halos, shaping structure while evading direct detection. Even gravitational waves produced by colossal collisions register only rarely. The void is active, Yet almost all of its motion, energy, and interaction occurs outside your instrument's reach. What is happening is real, yet fundamentally unobserved. Fields permeate space without manifesting directly. Electromagnetic, gravitational, and quantum fields influence matter and energy over vast distances. Fluctuations in these fields seed structure, drive formation, and govern evolution. Yet their subtle effects often escape measurement. You reconstruct their presence through consequences, never through direct observation. The universe's activity is largely silent, a background of forces and motions that maintain cosmic order while eluding perception. Even interactions between matter and radiation are vanishingly rare in the void. Collisions, emissions, and decays occur across incomprehensible volumes, yet the probability of detection is minimal. Your instruments are blind to the majority of these events. Large-scale flows, filamentary accretion, and the drift of galaxies occur without producing light or waves detectable across the intervening distances. The majority of cosmic motion is therefore hidden, producing a quiet universe that is active yet unobservable. This silence emphasizes the gap between existence and perception. You assume that what is real can be measured or observed, yet the void demonstrates that most of reality persists without any direct manifestation. Energy, mass, and motion continue beyond perception, shaping structure and evolution while remaining epistemically absent. The void is not empty in a physical sense, but it is largely inaccessible. A domain where the universe operates silently, without signal, without illumination, without detection. Ultimately, the silence of the void reveals the limits of observation. Space is filled with phenomena, interactions, and forces, yet most of them occur in domains beyond your instruments, beyond photons, beyond measurable gravity. The universe is vast, active, and structured, yet the majority of its processes unfold quietly, imperceptible to human senses or technology. What you detect, the stars, the galaxies, the radiation, is only a narrow sampling. The rest of reality operates in silence, shaping the cosmos while remaining forever hidden, a quiet expanse of influence that cannot be accessed, a universe mostly unobserved and largely unknowable. The terrifying implication. When you step back and consider all the evidence, the dark matter, dark energy, cosmic expansion, horizon limits, you confront the fact that what you see is the exception, not the rule. Most of the universe is inaccessible, unobservable, and fundamentally alien to experience. Reality is far larger, quieter, and stranger than your senses allow, and you are forever confined to the sliver that reaches you. The cosmos you perceive is a limited domain, defined by the finite speed of light, the age of the universe, and the accelerating expansion of space. Galaxies beyond your horizon recede faster than photons can traverse the intervening void, rendering them permanently unreachable. Even regions within the observable universe are dominated by dark matter and dark energy, components that shape every motion, flow, and structure without ever revealing themselves. The luminous matter you observe, stars, galaxies, nebulae, is a minority, a sparse trace of the universe's true composition. Expansion ensures that your observable patch is shrinking in significance. As space continues to accelerate, the vast majority of galaxies will slip beyond causal contact, leaving isolated islands of matter in a growing sea of inaccessible void. The light that does reach you is an echo from the past, often billions of years old, mapping only a tiny fraction of what exists. Beyond this, an unmeasurable expanse persists, obeying the same physical laws, yet entirely unobservable, fundamentally alien to any direct experience. Dark energy compounds the alienness. It dominates the universe's energy budget, driving accelerated expansion, yet produces no detectable signal beyond its effect on space-time. Its presence ensures that the cosmos is structured in a way that isolates regions, segregates matter, and prevents long-term interaction between distant domains. What you can see is a temporary, local consequence of conditions that no longer apply universally. The majority of reality is moving beyond observation, slipping into a state where its influence is negligible and its existence is silent. Dark matter presents a parallel mystery. It is pervasive, structuring galaxies and clusters, but cannot be observed directly. Its influence is inferred through gravitational effects, lensing, and motions of luminous matter. What dominates the universe's architecture is therefore fundamentally invisible. You measure consequences, but the substance itself remains alien. A shadow that guides the formation and evolution of structures without ever revealing its nature. Most of the universe's mass, most of its organizing principle, exists beyond perception. Even the flow of time and causality is constrained by these limits. The horizon prevents you from witnessing processes outside your light cone. Regions that shape structure may do so without any direct interaction with what you can measure. Events occur without transmitting influence. Correlations emerge without causal contact. And the large-scale coherence of the cosmos is established by mechanisms you cannot observe. Your perception is confined to a fraction of space, a sliver of causally connected reality amid an immense, silent expanse. Ultimately, the terrifying implication is epistemic as much as physical. You inhabit a universe where the majority of existence is silent, invisible, and fundamentally inaccessible. Structures, energy, and processes operate beyond detection, shaping reality without revealing themselves. The light you see, the gravitational effects you measure, and the phenomena you can detect are all exceptional. They are a minority, the illuminated portion of a cosmos that is largely hidden, moving, evolving, and existing without ever intersecting your perception. Reality is far larger than your senses, more structured than your instruments, and more alien than any direct observation suggests. The universe is mostly dark, mostly quiet, and mostly unreachable. What you measure is a fragment, a narrow intersection of light and matter, temporarily visible against a background of shadow, silence, and isolation. Everything beyond that fragment exists without ever communicating with you. You are confined to the observable, forever limited to a slender, luminous slice of a universe that is otherwise vast, inaccessible, and fundamentally unknowable.